This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 3, Boilers and Furnaces, Combustion, Efficiency, and Fuel Types. Here's the key framing. The handbook prints no boiler or furnace as a named object. The physics that governs both is combustion in Chapter 10. So we treat it as combustion applied to a boiler, a fuel's heating value, the air it needs, and the efficiency that ties the useful heat delivered to the fuel you burned. We'll read the heating value table, set the air balance, and work an efficiency problem. Concept 1. A boiler is a combustion chamber. A boiler heats water, a furnace heats air, and neither is a handbook object. Both are the same physics. You burn a fuel with air, and the released heat splits two ways: the useful heat you transfer to the water or air, and the stack loss, hot flue gas that goes up the chimney, carrying heat you paid for but didn't capture. Three levers decide how much you keep: the fuel's heating value, the air you supply, and the combustion efficiency. Concept 2. Heating value, gross versus net. Burning any hydrogen-bearing fuel makes water vapor, and that vapor carries latent heat. So the higher heating value counts that latent heat. It assumes the product water condenses back to liquid, and the lower heating value excludes it, letting the water leave as vapor. Read the table. Methane's higher value is about 10% above its lower value, and hydrogen's gap is bigger still, because hydrogen-rich fuels make the most water. Which basis you use will decide the efficiency you report. Concept 3. Air, theoretical versus excess. Combustion needs oxygen, delivered as air, which the handbook models as 21% oxygen and 79% nitrogen by volume. It balances the reactions. Carbon plus oxygen goes to carbon dioxide, and hydrogen plus half an oxygen goes to water. The air those reactions demand exactly is the theoretical or stoichiometric air. Real burners supply more to finish combustion, and the excess air is the extra, measured against the theoretical air. Too little air leaves unburned fuel and carbon monoxide. Too much just heats inert nitrogen and throws it up the stack. Concept 4. The flue gas link. You can't meter theoretical air directly, but you can sample the flue gas. As excess air rises, it dilutes the products, so the measured CO2 falls below the fuel's stoichiometric maximum. The handbook backfigures that maximum from a dry flue gas analysis, using the measured CO2 and oxygen. Natural gas peaks near 12% CO2 at zero excess air, and drops toward 10% at 20% excess. That falling CO2 is the fingerprint of excess air. Setup. Combustion or thermal efficiency. It compares the heat you keep to the heat the fuel carried in, and the handbook gives two equivalent forms: useful heat over heating value of fuel, or 1 minus the flue loss over the heat available. The handbook defines QH as the higher heating value, fuel rate times HHV, and QFL as the flue loss. Our boiler burns natural gas at a higher heating value of 1,000 BTU per cubic foot at 10,000 cubic feet an hour, delivering 8 million BTU per hour of useful heat. Theoretical air for natural gas is 9.6 cubic feet per cubic foot. The burner supplies 12. Solve Part 1. Combustion efficiency. The heat available in the fuel is the rate times the higher heating value. Efficiency is the useful heat over that, which comes out to 80%. Stack loss is the balance. 20% of the fuel energy goes up the chimney. Note the basis. Had we used the lower heating value in the denominator, the same boiler would read about 89%. Report efficiency on the same basis as the heating value you used. Solve Part 2. Excess air. It's the extra air over theoretical, divided by theoretical. 2.4 over 9.6 is 25%. Watch the denominator. Divide by the air supplied instead, and you'd get 20%, which is the distractor the exam plants. And remember the coupling. Excess air finishes combustion, but every extra cubic foot is heated and thrown up the stack. So raising excess air lowers the efficiency we just found. Traps. 4. 1. Higher versus lower heating value in the denominator. The lower value inflates efficiency by about 10% for gas, and condensing units can even top 100% on that basis. But the handbook defines QH as the higher heating value, so use it unless told otherwise. 2. Excess air divides by theoretical air, not by the air supplied. 3. The efficiency loss is the stack loss. More excess air means more flue loss and lower efficiency. 4. Air is 21% oxygen, 79% nitrogen. That nitrogen is inert ballast that soaks up heat and leaves in the flue. Quick recall. Heating value comes gross or net. Higher includes the latent heat, lower doesn't. Air is 21% oxygen, 79% nitrogen. Excess air is the extra over theoretical divided by theoretical. The flue check back figures theoretical CO2 from the stack analysis. And efficiency is 1 minus the flue loss over the heat available, with QH the higher heating value. Golden rule, keep the heating value basis consistent and measure excess air against theoretical air. Next up, Lesson 4, Heat Exchangers, the LMTD method. Combustion released the heat, now we move it. We turn to the shell and tube exchanger that carries heat between two fluid streams. The rate equals the overall coefficient times area times a correction factor times the log mean temperature difference, with the overall coefficient built from film resistances and fouling. Same goal, a different tool. And note it lives in Chapter 5, Heat Transfer, not Chapter 9. Everything's at peprepengine.com, cheat sheet, work solutions, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.